Well, dear colleagues, I like to welcome you for the second day of our conference. The first speaker, invited speaker, who will present, in my opinion, one of the most important topics of the recent years. It is Armen Aghajanyan from FAIR, and I would like to welcome him, at least virtually, from here, from Yerevan. And Armen, please welcome. The floor is yours.
Hey, thank you for having me. Awesome. Okay, perfect. Okay, yeah. Thank you for an introduction. I've been at FAIR for a couple of years now. My main focus has been on language models, I guess not too surprisingly, and then like more in-depth multimodal language models. So today we're just going to talk about the LM space in general, what scaling laws are and why I think they're very important, and then kind of the big question, what is the future of AI research? In general, I think this is a quite, opinionated presentation, so we'll leave some time for questions. This is about a 30-minute presentation. So yeah, I guess let's start. So kind of a refresher on what we mean by large language models, and this is something that I think this slide I update every couple of months at this point. So at least internally, when we talk about a large language model, we usually talk about something that has more than 30 billion parameters if we have a dense model, and usually training on something like 400 billion tokens. Language models, I'm sure you all know, but for a quick refresher, you're pretty much just modeling the log likelihood of a document, of a piece of text, and you break it down with the chain rule and you model token by token. And when we talk about models, I think it's pretty ubiquitous to just talk about transformers. And pretty much everyone I know that is scaling transformers is scaling one specific variant from the 2017 paper. This is just the post-norm variant of the classical attention is all you need paper. And so, again, I'm sure you guys all know this, but just as a refresher, if you train these very, very large language models, you unlock the capability to do some really cool stuff. So primarily, you're able to do this in-context learning. So you can pretty much give a description of the task with examples or without examples. We'll distinguish case shot versus zero shot. And the model is capable of doing inference without needing any significant fine-tuning procedure. And then when you have large language models, you can start having very fancy ways of prompting them. For standard prompting, for example, you can kind of directly ask the question. For chain of thought prompting, which was kind of a new thing that came out, you can ask the model to explain itself or give reasoning for why it gave an answer. So kind of very trivial techniques that yield very good results. And there's been a ton of work, and I'm including some from our group as well as the self-ask work from Ophir Press. So there's a ton of ways that you can kind of prompt these models and you get like very incredible results, right? And at the core of the success of large language models fundamentally is scale, right? So the question that we have to ask is, what is the correct way to scale? And this is a very, very non-trivial question, right? There are many things to consider here, right? From what is the correct parameterization, right? Do we want deep versus wide? Do we want more attention heads or do we want larger embedding spaces? How do we balance out the compute that's in the attention or the feed forward layers? Where do we put layer norm, things like that, right? And then there's even more fundamental questions, like training these things is incredibly expensive, right? So if you have some fixed compute budget, can I figure out what the optimal parameter budget is? Can we figure out how to train these optimal models, right? And then there's other questions, right? Which is, okay, you scale up and you need to scale up on something. So how do you balance out the data, right? And this is a fundamental kind of question and something that I actually think a lot of the open source reproductions of language models get quite wrong most of the time. And so I make this claim, and I've made this claim quite a bit, which is that as of now, scaling large language models, it's an art. It's not fundamentally a science. And the question that we should all be asking is, how do we make it a science, right? So everything that we do right now is based off of gut intuition, right? If you want to ramp someone up on large language model training, right, I'm just giving like some of the internal statistics that we have. a very conservative estimate is that the cost to do this is between 10 and 30 million. If you look at like Azure or AWS credits, right? So it's an incredibly hard thing to ramp people up on. Debugging model training is not formalized, right? We have no theory about why any of this works. So in the lack of theory, you kind of trust the senior research scientist who knows what they're doing, right? And then there are even kind of more systemic problems, like distributed computing is actually very, very hard. You know, when you're training on 2,000 GPUs, if one or two GPUs dies, everything collapses, right? So how you get like what we call resilient training is a very non-trivial hardware, software, distributed computing problem. And I'm going to make this claim that no one knows exactly what they're doing. So anyone that says that they know and they fully understand language models is lying to you. And because of this, there's kind of a reason, if you look at the large language model startup space, you pretty much only have people from big tech, because it's really expensive, right? Like you don't want to join a startup and spend $30 million to learn something before you train anything, right? And so, for example, I'm listing out the kind of the core competitors to OpenAI that I see here. Character AI, which honestly is just a ton of people from FAIR that left. So really, really smart people like Maya Lott and Stephen Roller. Anthropic has people from GPT-3. Adept has people that wrote the original Transformer paper, and same with Cohere. So yeah, so if you're starting a language model company, my recommendation to you is to join big tech and burn a lot of money there to figure out what you're doing, and then start your company. So to give you a little bit more intuition, what I mean by this is an art, I want to kind of tell two stories that are real stories from work, about the complexities of training these models. So this is an example of one of our junior scientists. He's very, very hardworking. He pings me at 2 a.m. And for some reason, he's seeing that kind of the standard OPT, if you know OPT, this was kind of a model before Llama that was released by our group. And so he's seeing that there are kind of very poor convergence properties. And so how do we kind of debug this, right? And so this is me just going down the list with him of possible things that it can be. We're looking at kind of the automatic mixed precision strategy, right? We're talking about what the loss scaling looks like, because he was using FP16, whether or not the activation norms are growing. And so yeah, I kind of always reiterate this, that, you know, this is all guesswork. Like I'm just guessing, right? Further, I see that, you know, some of his hyperparameters are a little bit off. His Armen betas were a little bit off. I asked him to remove some stuff, and then all of a sudden you get kind of this really nice convergence, right? I could not tell you why, for any reason, that like we picked these parameters. This is complete guesswork, right? And this just comes from intuition from training a lot of these models. And in that sense, this is kind of a complete art, right? There's nothing theoretical or mathematically grounded here. Like I'm just guessing. It turned out that my guess this time was right. And then when you get to kind of very large scale, right, we're talking like 2,000 GPUs, there's kind of this very, very long tail of problems in large distributed computing. So this was a big model that we were training on 2K GPUs, I think last summer. And all of a sudden, for about 2 or 3 weeks, our throughput in the models was all over the place, as you can see. Now the thing is you know, when you're dropping, I don't know, 25%, that's kind of a significant drop. It's kind of hard to train models, and then there's instability, so you have to, you know, restart models constantly. We wanted to understand what was going on here, right? So we went and we kind of talked with our cloud service provider for about 2 weeks. We pretty much ruled out everything that it could have possibly been. We looked at the training code, we looked at saturation, we looked at memory transfer bottlenecks, we looked at all the device drivers, we reached out to the internal PyTorch team to see if there were some fundamental bugs in PyTorch. And we did this for 2 weeks. And after 2 weeks, it magically resolved itself. And then it turned out the reason was because the actual like DGX machines, the actual the cloud was in Phoenix, Arizona. Now, if you don't know Phoenix, Arizona is incredibly hot. So in the summer, it gets like 45 to 50 degrees Celsius. It's like insanely hot, right? and they decided to build this cluster there. And so it turned out that there was a heat wave that was going on in Phoenix that was causing all of our jobs to kind of crash, right? And so after that, in our experiment tracking, we include the temperature of our kind of the weather of where the cluster is, right? So this is like a super, super absurd story. And in order to figure out if this was actually the case, we had to ask the service provider to put the equipment in an actual oven so we could reproduce the Arizona climate, right? And then we figured out that this is actually the cause of this issue, right? So this is like, there's such a long tail of problems that can arise, and it significantly complicates something that at the surface level seems trivial, this large language model training, right? So now that I've kind of told you that this is an art, you know, the next step is we're trying to make this a science. And so the very first thing in order to make it a science is to see if you can have some predictive capabilities of like some macroscopic symptoms of the language model, right? So this all started kind of from Kaplan's paper. So this was the first scaling law paper that was put out from OpenAI. And the question that was being asked was very simple. So can you predict the expected loss if you know the model size, or if you know the data set size, or if you know the compute size? One of these three, no combinations of them, right? And so OpenAI, they did a ton of experiments and they figured out that things kind of follow this power law distribution, and that you can actually predict what the loss will be. And so this becomes a very useful thing, because before even training the language model, presumably you know what the end loss should be. So if you know what the end loss should be, if things are looking a little weird, you probably know that your run is not going great and that you need to fix something, right? And so this kind of sparked a whole lot of work from maybe 3 or 4 labs that have probably too much money to spend on this. And next came out these chinchilla scaling laws. So the chinchilla scaling laws fundamentally answer this question that can we predict what the expected loss will be if you know the model size and the data set size? And so they modeled it kind of, they realized that there were limitations with the power law parameterization. So they modeled it in this kind of approximation, and it kind of, to me, makes a lot of sense, right? So the very first term says, you know, this is the minimal achievable loss that you can get on this data set. Like, it's the minimal informational entropy of this data set. And then there's some approximation errors because our models aren't perfect and our optimization isn't perfect. So you have this functional approximation error that pretty much is a function of the number of parameters in the model. So, you know, presumably your functional error should decrease, you know, as your model size grows. And some convergence error, which is a cause because, you know, we don't have the perfect optimization methods. And this also kind of decreases with the size of the data set, right? So the recipe here is just increase model size, increase data set size, and they get what they call these compute optimal scaling laws. So pretty much what this means is, if you can answer this question, you can answer kind of a follow-up question, which is, if you have a compute budget, can you tell me what model size and what data set size is optimal? And it turns out the answer is yes. So these are the chinchilla models. They're called compute optimal models. And so we thought this was very cool. But one thing that no one kind of talked about was that the underlying data set fundamentally changes the scaling laws. And because the data sets are hidden from us, because these are, you know, humongous companies, you can't really use these coefficients unless you're training on the same exact data. So we actually wanted to extend out and kind of generalize, apart from just text data sets, to general modalities. And so this is kind of what our recent paper was about. And I'm going to call out, this was also a collaboration with Aghajanyan, which is local to you guys as well. And so we started out by pretty much replicating chinchilla scaling laws for different modalities. So I think we picked 7 modalities, you know, unconditional image generation, conditional image generation like DALL-E, text, speech and text, which is like ASR or TTS, text-to-speech or speech recognition, unconditional speech code, and molecules. So the very first step for us was, you know, we produced these chinchilla-like scaling laws for all the modalities. And if you look at the actual coefficients, they're fundamentally different for each modality. So you kind of can't make any predictions about the chinchilla scaling laws, right? Like, you can't say that, you know, for this compute budget, if you're training on images, that the chinchilla scaling laws will transfer over. But our paper kind of gives you this recipe. And so then we asked the question, right? Like, let's say we train a model by concatenating two data sets. So we concatenate unconditional speech and unconditional text. What should we expect the scaling law? One, what should the scaling law look like? And two, what do we think the kind of optimal parameterization of the scaling law is? And so we propose to keep things really simple and continue on the chinchilla parameterization because it looks really, really nice, right? And we came with this parameterization in our paper. Pretty much, what would the loss look like if the data sets were modeled independently? Subtract out this very fundamental term that pretty much says what is the maximal level of synergy between the two modalities. So you can also kind of, like, if you squint your eyes and you're not too mathematical, you can think of this as being like the mutual information of the two domains. And of course, you're going to get some type of competition between the two modalities in the functional approximation space, which is a function of the number of parameters, and you'll get competition in the optimization process, right? So we came up with this parameterization, and then kind of it turns out that it fits the data very, very well. And then if you kind of, again, go and you run an insane amount of experiments across model sizes up to 7 billion, you'll notice that, again, even the mixed modal scaling laws are very, very different from each other. Now, the really, really cool thing that we can say is that, you know, if we are reducing the loss beyond the independent modeling of the modalities, we are synergistic. So pretty much we're extracting information from the two modalities that you wouldn't get if you trained on each modality separately. And so this is a really cool thing. And people always talk about like grounded text generation with the presumption that if you train on images, you'll get better perplexity. But no one really did that. And that was one of the goals of this paper, was to actually show that we can do that. So we can say we have synergy if this parameter, this synergy parameter, is greater than the functional approximation error in addition with the with the addition of the optimization error, right? And so we said, okay, let's try to see if we can break what we call this competition barrier. Is it possible to actually show that there can be synergy between two modalities when you train together, right? And so we went and we kind of plotted out what the competition barrier should look like, right? And so the competition barrier here is this black line. So this is predicted from our scaling laws. And we said, okay, we want to show empirically that these scaling laws are actually highly predictive of these non-trivial emergent phenomena, right? So let's pick kind of the cheapest experiment that we can, and see if we can actually show that these scaling laws are quite predictive. So the cheapest that we kind of visually saw was this speech text, which kind of makes sense, right? And we said, okay, let's minimize the flop utilization. And so the 6ND, where N is the number of parameters, D is the number of tokens, is a very crude approximation to the number of flops to train, such that we lie somewhere on this competition barrier, right? So if you do that for speech, we found out that, okay, you need to train roughly a 30 billion model on roughly 45 billion tokens. So we said, you know what, we're a little scared that our scaling laws, they're not exact. So we added some buffer space. So I think N was like 30 or 35 billion and D was 50 billion, were these number of tokens. And we trained this model. And so we saw something really, really cool, which was, we actually did end up breaking this competition barrier. So one, this was kind of the very first case that we showed that, two modalities independently can be grounded. The only thing that's in our way is just scale. And two, that these very complex scaling laws can actually be predictive of non-trivial macroscopic behavior, which was kind of very exciting for us, right? And then we said, okay, like this is really cool, but can scaling laws tell us anything more about how to properly train these language models, right? And so we said, okay, let's look at some fundamental phenomena that we occur, that occurs, and let's see if we can predict things, right? So one thing that we saw, we call this intermittent coordinate descent-like training. I think this is a very complicated and formal term. Pretty much what we see is that if you're modeling on multiple modalities, there will be kind of very long periods of time where one modality is pretty much flat when you're training. And we kind of don't have an idea why this happens. But interestingly enough, this ends up correlating with scale, and it correlates with this alpha ij hyperparameter that pretty much tells you how much competition there is in the functional approximation, right? And so it turns out that we can actually even predict these types of phenomena just by looking at the scaling law coefficients, which is a very, very cool thing to be able to do. Even further, we were looking at trying to figure out if we can predict optimal hyperparameters. So we started looking at, okay, can we actually predict optimal batch size? So we did this huge sweep for one of the models, found the optimal batch size with a fixed compute budget, and we found that it actually correlates with beta ij, which is this hyperparameter that tells you how much competition there is in the optimization process. I actually think this is wrong, so don't look at this definition. But pretty much now we can say that, if you're training on like the image text modality, which is something like DALI 1, your batch size should be 8 million, right? 8 million tokens per batch, right? So now we're getting into the space of we can actually make very, very good guesses about what the optimal hyperparameters will be. Now, what's very non-trivial about this is that the scaling laws were trained with non-optimal batch sizes, and yet the hyperparameters are predictive of optimal batch size. Again, I have no idea why this happens. It does happen, and practically it's very useful. And I will kind of show you a sneak peek of our current work to show you why this is kind of so cool. If you've ever trained language models, you know that there are some other fundamental issues, such as gradient spikes. So gradient spikes can throw away your whole training. And so intuitively, we knew that the number of gradient spikes grows with the model size. So that kind of makes sense. And then it turns out that when you actually plot the number of parameters that your model has divided by this alpha ij parameter, which again, just to reiterate, is some coefficient that tells you how much competition there is in the functional approximation, you get this very, very good linear fit that will tell you, even before you start training, how many gradient spikes you should expect to see. And this is super useful, right? So if you're training a model and the amount of gradient spikes is way beyond what these scaling laws predict, you're probably doing something something wrong. So again, you have to go back to the senior scientists and try to figure out what's going on. So now kind of in our toolbox, we have significantly more kind of debugging tools that we can use to actually train language models. And to us, this was really, really cool. And so that's just kind of like a very dumb experiment. I said, you know what, let me go back to one of our one of my interns' papers, which is this RSCM3 work. And the thing was, in this paper, he trained this model himself. I was kind of busy in the summer. So this model was for sure not optimal. It was not optimally trained. So I said, okay, like if we go and we apply our scaling laws that we have and all the learnings that we have from this paper, how good of a model can we actually train? And so what we saw was that using these scaling laws, using everything we learned and having like a proper training done, you can kind of get a significant like 10x improvement in quality. So we beat out his 2.7 billion model with a 350 million model quite significantly on FID. And so this got me kind of excited. I have my personal gripes against diffusion models. So I said, okay, let's just try to scale this up and see if we can kind of be very, very competitive with the state-of-the-art diffusion models. And so it turns out, yes, if you know how to properly train them, like our 7 billion model, that's just boring DALI 1. We do some data augmentation, but it's like a super boring, just properly trained language model. Turns out getting kind of the second lowest FID score that is kind of known. So we're just behind Reimagine. And by the way, Reimagine used an insane amount of compute because it was also based off of ImageGen. So pretty much in a very dumb way, without doing all these like crazy diffusion things, just training a very boring language model, knowing the proper way to train things, we're able to get pretty much state-of-the-art in text image generation in like a very, very boring way, right? No research breakthroughs here, right? And so let me show you a couple more. These are all prompts from ImageGen and the party paper from Google, both of which we beat out, by the way. Yeah, so I think quality is quite good. I guess that's what I'm trying to show. And then this is kind of a sneak peek. We'll release a paper in a month about this, but we actually showed that instruction tuning language models, which is just tuning on very high quality data, it's kind of a general recipe. It's not just a text recipe. So we instruction tune on some instruct pix-to-pix data, and we showed that, you know, this works very easily too, right? So you no longer have to have like these incredibly complex diffusion papers that try to like do model surgery on stable diffusion to get this to work. You just instruction tune in a very dumb way, and things just work, right? And yeah, this is kind of a very general recipe. Apart from just instructions, you can go from scribble, from lines, from human pose, from segments. You can do instruction tuning is like this very general recipe. And this paper will come out in probably by NeurIPS, I think. Cool. So I've kind of walked through why I think scaling laws are important and kind of give an introduction to some current work that we have. So let me I guess make some claims that hopefully people will disagree with me on, and we can have a discussion in roughly 5 minutes. Yeah, I think I have 5 minutes. So what is the future of AI research? So this is a question I get from my interns quite a bit, and this is my kind of very, very pessimistic answer. I think traditional niche domains of AI research are pretty much dead. Semantic parsing is dead. I say this as someone that worked on semantic parsing for a couple of years. Dialogue, reasoning, question answering, MRC, summarization, pretty much every like vertical task that you can think of with text, I think is solved or will be solved in the next year. Mixed modal language modeling is kind of the next step, right? So we kind of see hints of this from GPT-4, right? They take images as input, but they don't generate out images, right? They don't take speech as input, they don't generate speech out, right? So there still is this kind of universal foundational model sometime in the future that will be able to deal with any modality. And this is what my team is kind of working on now. And so when we talk about research directions, I think the single most impactful direction that we can ask for is this science of efficient scaling, is what we call it. So how do we make the scaling law coefficients larger? How do we improve how quickly we can train these models? And so if you kind of break it down, there's 5 directions that kind of form the basis of all research here. So the first one is kind of a very system level thing, which is like, can you give me a better transformer implementation? To be honest, this is like very low risk, and I also think it's very low impact. So to give you some context, like the code base that we've developed, the one that we've built, Metaseq is open source. You can go take a look at it. It gets 60% mean flop utilization. So it achieves 60% of the theoretical utilization that you can get on A100s, right? So let's say you go and you're a PyTorch genius, and then you get it to 100%. Like, okay, you improve scaling laws by 2x, right? It's not a fundamental difference, right? And the highest I think that has been achieved was from our friends in Character AI. They did some crazy engineering, and they're getting somewhere around 80% mean flop utilization. So it's like a 20% improvement, which is important if you're a startup, I guess, not too important if you can spend big text money. So I wouldn't necessarily go in that direction. Architecture improvements, very high risk, very high reward. I don't see anything beating out transformers in the short term. There have been 200 versions of the transformer paper written. We still use the original one from 2017. And when you ask why, I think like there's nothing fundamentally wrong with attention, with transformers, right? Like with convolutions, with RNNs, there was always something that was fundamentally wrong, whether it was like the receptive field, or you have ON where N is the sequence length during training for RNNs, so it was slow. There was always something wrong, but there's nothing that's fundamentally wrong with transformers. The one thing that maybe you could say is context length, because attention is expensive. But for anyone that trains large language models, you actually know that attention is not that expensive. So if you're training a 175 billion parameter model, attention takes about like 5% of the total flops. Like the majority of flops are in the matrix multiplications. And that's why it's actually so compute optimal, right? Because these GPUs, that's the one thing they're really, really good at. So it's tough to beat that. Better data selection is kind of my favorite personally. So everyone so far has been doing IID, random sample the data pre-training, instruction tuning on high quality data sets, and RLHF, which is another thing I don't necessarily believe in, but there are better ways of curating the data for pre-training. there, and the next slide will show some of the research that we're doing here too. But this is like, I think this is a super ripe research direction that not a lot of people are looking into. And this will probably give, I think, the highest return on investment for research here. Better objective. Like, do we think we're done with log likelihood? Are we done with perplexity? Yeah, high risk, high reward, I think. I think it's quite hard to beat any type of autoregressive objective. I think at the end of the day, the compute's going to be king here. Diffusion models for text, I don't think they can work. We've tried hard to get them to work. I think there are foundational reasons why they will never work on text. But yeah, kind of cool direction to look into. Better optimization, high risk. My guess is it's an okay reward. High risk because kind of the same story as transformers. We still use Armen. I guess we use Armen with the fixed, pretty much the fixed Armen from like 2018, I think. Better optimization is interesting. The reason I say that there's an okay reward is there is kind of a lower bound of information, or an upper bound of information that you can squeeze out from a couple of data points, right, from a single batch. The question is, how far away are you? And I don't think we're that far away from the optimal kind of extraction that you can get. And this is just a gut feeling from trying out a ton of different optimizers, and we had some internal ablations as well. So I also want to look into that because my optimization theory isn't that strong, but also a very cool direction if that's where your strengths lie. I know I'm a little over time, but very quickly I want to talk about kind of again why I think the data selection is kind of a very interesting research direction. So if you would take a look at this kind of center plot, this is the validation set on standard benchmarks in large language modeling, such as MMLU or Big Bench or Eleuther AI's evaluation harness. And so pretty much what we show here is that if you do a very clever data selection, you can prune at a significantly improved data rate. And so this is something very quickly that we put together, and it turns out that it works quite well. I think this paper will come out in 2 weeks or so, but data is kind of the low-hanging fruit for improving large language models. So yeah, kind of a lot of info compressed into this presentation, but I wanted to leave, I think, 15 minutes, if we have time for that, for questions, and just open up the table to a discussion.
Yeah, thank you. It was really great talk. I have a lot of questions myself, but I need to pass the mic for the other questions. Do we have right now?
Yeah, thank you for your presentation. On the last slide, I saw that there was a graph, and this were like the duplicating, and the perplexity is lower. Is this right?
Yes.
Yeah. I've read a paper just like a week ago. It was Pythia, and they were making such an experiments, and they have showed that the duplicating isn't making perplexity lower. Have you seen it?
Yeah. So deduplication is kind of an interesting phenomenon when people argue whether you should duplicate or should not. Now, the problem at the end of the day lies in how you're evaluating, right? So if you deduplicate the training data, but don't deduplicate the validation set, you're going to get worse perplexities, right? Just because you're going to miss the head of the distribution, which appears a lot, right? So usually when these papers, I think usually get validation kind of wrong. So one thing that we're doing is we want to look at the perplexity on data that is representative of downstream tasks, which is why I like looking at like MMLU or Big Bench data. The other point is that when you look at deduping, the standard deduping is like the GPT-3 way of using like min LSH hashes to dedupe. What we're proposing is kind of some new metrics based off of clustering in the latent space of like BERT or something. So these types of dedupe methods usually outshine like purely kind of n-gram overlap based dedupe methods. Yeah, I hope that answers your question, because yeah, there's a ton.
Yeah,
There's
thank
papers that say deduplicating helps a lot. Others say that it doesn't. But yeah, I don't trust the validation sets of those papers. Like sometimes it's okay to have a higher perplexity, right? Like you don't want to have a high perplexity on bad data, right? Like you don't want to have a low perplexity on bad data, right? So sometimes it's okay.
Okay, thank you. Next question. While people are thinking, I have a question myself. You have been talking about data and data selection, and it happens that I'm also working on this problem a bit in the same direction, but I have a question in maybe different way. So you have shown at some slides that you can, for example, predict the loss of the model given the size of the data set. But don't you think that the data set nature itself is really important here? So like even the text data is not that homogeneous, I would say. So it doesn't depend on the nature of the data, not only the modalities, but inside the modality also.
Yeah, 100%. Yeah, that's kind of what I was saying. Like, you can't just apply chinchilla scaling laws to your work, right? Because you don't know what the underlying text data was. In the future, I think like the most optimal scaling law paper would be a scaling law that considers 1, core hyperparameters, and 2, has some magical information theoretic property of the data, right? And that will be baked into the scaling law. So modality, I think, is kind of an arbitrary distinction. I think the reason we split it by modalities is because we didn't know what this information theoretic property is, right? But presumably there is one that will let you kind of generalize across modalities and say that, you know, like I have a data set that has, you know, property X value of 0.2, like this is what my scaling laws will look like. I think this will be like the greatest scaling law paper ever. I don't know what that information theoretic property is. Like, modeling images is fundamentally different from modeling text, right? Like, images have significantly more modes than text does. And because of that, you kind of have to alter the way that you train these language models. So I'm not sure what these distributional properties will be, but that's like a super cool area of research, I think.
Yeah, thank you. The next question regarding your description of these information theory properties of the data. You have shown that we can think of the optimization like 2 modalities are battling for the let me see for the weights of the model, so for the capacity of the model. So is it how do you think, is it caused by the representation of the data we use or the nature of the data? So you're saying that it's only the information theory which could help us here, but maybe you have some insights on that.
Yeah, I'm not going to give you a great answer. I don't know what the source of competition is, right? So competition is kind of an interesting term. So a lot of times translation papers actually talked about competition, like way back, maybe not even way back, 4 or 5 years, right? They talked about if you have a single model that's translating from multiple languages to multiple languages, there's competition between the different languages, right? And I think about like 6 months ago, one of Omer Levy's students from Tel Aviv University put out this paper that said, you know, competition is only problematic at a small scale. So if you actually scale up translation models, there's not really competition between languages, there's actually synergy. I think that we cite them in our paper as well. So I don't know what competition fundamentally means here, right? Like, it might be a weakness of the model not being able to find the right alignment in some very complex latent space, right? And if you train larger models, presumably the alignment is easier to find. It could be something fundamental like that. I think this is kind of distinct from the information theoretic properties, although presumably if you have some level of mutual information, you could maybe make some predictions. I'm not sure. But yeah, competition is, I can't give you a good answer here. This is also kind of an intuitive feel for what it is.
Okay, thank you. Maybe some additional questions from other guys, because I have a lot, but maybe someone also could have from maybe from online. Anyone?
So thank you for the presentation, and I would like to ask about deaths of traditional tasks. Can you maybe more explain? So he has semantic parsing. So what is this? It means that everything can be done by current language models, or what's from what side? This, please explain.
Yeah, this gets brought up always. Okay, I'm gonna give you an anecdote, right? So Google put out this Palm paper. I don't know if you've seen this, but this was a 540 billion parameter model that they trained. And the paper's huge, like Google papers are, right? It's like 100 pages. But if you go and you carefully look in the appendix, there's one section where they look at this zero-shot machine translation. And if you look at this, a model that was trained without any explicit aligned translation data, this model was outperforming Google Translate. And Google Translate, has like 20 or 30 people dedicated for like 15 years trying to figure out how to do optimal machine translation. So you pretty much have a model that just when it was scaled up enough without any explicit alignment or translation data was outperforming a production level system that has been being fine-tuned for 15 years. So when you look at something like that, you realize that most likely these vertical domains, these tasks that are kind of, I don't know how to say this, they're singular tasks, right, are probably all going to be replaced with language models. And because of that, like I personally will not recommend to be looking into these research fields anymore. Like semantic parsing, I built like my very first task when I joined back when it was Facebook was to build out their like semantic parsing platform for their future assistant. And then we shipped this out. And I remember I worked on this for like 6 to 8 months. We worked on this model. And recently we tried out one of our internal language models and it just blew everything out of the water. And the thing is, it wasn't even trained on semantic parsing data, right, at all. And so anyway, the production team went and then instruction tuning on semantic parsing and got really good, right? But in general, I think the pipeline for most of these tasks is already kind of well defined. I think it's going to be very, very hard to beat. I hope that answers your question.
Yeah, I think it answers the question, but I have short following questions. I think we have a few minutes more. So you said that you used one of the internal language models, but as far as I understand, at least from my experience, these internal language models we have, they're totally huge, like, I don't know, thousands of GPUs to train and at least dozens to just run. And don't you think that you cannot use such a huge power for like for small tasks, even the small task is the dialogue? So don't you think that we should try to use smaller models for day-to-day product usage?
Yeah, I mean, take the Llama model. Are you familiar with the Llama models from Facebook or from Meta? There were a family of language models released. It starts off from 7 billion. Like, let's say you have semantic parsing data set, right? Like 10,000 data points, 20,000 data points, right? Or dialogue or whatever it is. You can take the open source Llama model, you can fine tune it on, or instruction tune it, supervised fine tune it on your dialogue data, all for the cost of about a couple $100 on AWS, right? And this model will outperform you spending 6 months taking BART, fine-tuning on your dialogue data, trying all these fancy fine-tuning tricks, right? And so in that sense, kind of the ROI doesn't make that much sense anymore. The problem is then you kind of become, the risk is how fast the open source models will grow. And that is a risk. But there are still groups working on it. And I do think even just the Llama models that you have now are very, very competitive. They're also very efficient implementations of things like Llama, right? That like on a MacBook can run like a token every 50 milliseconds. Like that's more than quick enough for dialogue tasks. I'm sure there are other tasks, like I can imagine computer vision tasks in certain domains, need to run, I don't know, 20, 30 milliseconds. Maybe then that's still a reason to be doing this, but you shouldn't really bet against hardware getting faster. So.
Okay, I see. Don't you think that even, I don't know, distillation on the specific task is will be helping us to work with the smaller models?
Yeah, distillation is a great thing. So I think kind of in machine learning, we operate with this, I think, incorrect notion that there's this symmetry between training procedures and inference procedures. Like the idea is that you need to use the same exact model architecture during training as you do in inference. And so the question is, why do we have this implicit symmetric assumption? Like it doesn't need to be there, right? And so one of the things is that like distillation is highly, highly effective, right? Like for example, if you told me you have to deploy a 7 billion model, what I would do is I would spend my compute training a 60 billion model and then distill it to a 7 billion. That would be more optimal than training a 7 billion model. And even then, like you don't need to keep the fundamental architecture, right? Like one thing that we tried out and works very well is you can move away from things like multi-head attention and move to things like multi-query attention. And so multi-query attention is usually like 5-6 times faster than multi-head attention. And so it turns out that you can do pre-training, get very, very good perplexities with multi-head attention, fine-tuned towards multi-query attention, giving you a 5x inference speed up. And that would outperform a model that's just trained with multi-query attention, pre-trained with multi-query attention, right? So I think the symmetry between training and inference needs to be broken. And distillation is a great example of how this can be broken.
Okay, it's really thought-provoking. Thank you. I think we have running out of time, so thank you. It was really great to have you here. And goodbye. Thank you.
Yeah, thank you. Bye.